Here's another example. This time, we need to find the indefinite integrals of the following expressions by integrating with respect to the variable t, as opposed to integrating with respect to the variable x like we've been doing up until this point. Most of the time anyway. So let's start with question 1, naturally. We need to integrate 3t squared with respect to t. So the integrand is this expression here, which is a function of t. You can think of 3t squared as the following expression: dy dt equals 3t squared. And we now need to integrate with respect to t to obtain y. So that's what's being done here. So we're integrating this expression, which is a function of t, or which is in terms of t rather, with respect to t. The same procedure applies. If you have something of the form ax to the n, integrating this gives ax to the n plus 1 divided by n plus 1 plus an arbitrary constant, provided n is not equal to minus 1. If you have something in the form at to the n, so I'm just changing the variable from x to t, the same procedure applies. Wherever you see x, you just put t. You get at to the n plus 1 divided by n plus 1 plus your arbitrary constant. So the integral of 3t squared, well, integrating 3t squared with respect to t simply gives, so this is equal to 3t to the power of 2 plus 1. So the index is increased by a unit of 1. You add 1 to the index and you divide by the new index and you add an arbitrary constant. So this gives 3t cubed divided by 3 plus the arbitrary constant, which is t cubed plus the arbitrary constant c. As simple as this. The second expression is as follows: 35 minus 2t plus 12t cubed. We need to integrate this expression with respect to the variable t. This is the integrand, which is bracketed. It will integrate in respect to t. So you can integrate each term with respect to t while noting down the signs. Minus, integrate 2t with respect to t, the plus sign. Then I'm going to integrate 12t cubed with respect to t. And here's what we get: 35t plus an arbitrary constant minus, when you integrate 2t with respect to t, what do you get? 2t to the power of 2 divided by 2 plus an arbitrary constant plus 12t to the 4 divided by 4 plus an arbitrary constant. And that gives 35, so I'm dropping brackets now, 35t plus c1 minus 2t squared over 2 minus c2 plus 12t to the 4 divided by 4 plus c3. So just in case anyone's still confused, 35 is the same thing as 35 times t to the 0. Anything to the 0 is 1. So we have something of the form at to the n. And integrating such an expression with respect to t gives at to the n plus 1 divided by n plus 1 plus an arbitrary constant. So integrating 35t to the 0 with respect to t gives 35 times t to the 0 plus 1, which is 1, divided by 1 plus an arbitrary constant. So that's how this was obtained. 35t to the 1 divided by 1 is something as 35t. And don't forget, when you have a bracket and minus sign outside a bracket expression, to drop the minus sign, you have to change the signs of each term. Instead of using a and b, I'm going to use something else. I'm going to use real numbers. So if you have something like 5 minus 7, if you want to drop the bracket, 5 becomes minus 5, minus 7 becomes plus 7. If you have something like 5 plus 2, to drop the bracket, 5 becomes minus 5 and plus 2 becomes minus 2. So this term can be simplified because 2 here 1, 2 here 1, 4 in 4 is 1, 4 in 12 is 3. So what we have is 35t plus c1 minus t squared minus c2 plus 3t to the 4 plus c3. Grouping like terms gives 35t minus t squared plus 3t to the 4 plus c1 minus c2 plus c3. And as you know, all the constants combine to give a single constant. So we have 35t minus t squared plus 3t to the power of 4 plus a single constant which I'm going to call c. So I'm saying c1 minus c2 plus c3 is c. And we're done. So this is the indefinite integral. This is the indefinite integral of this expression here. So here's question 3. We need to integrate 6 with respect to t. Integrating 6 with respect to t. So what is the next step? Well, one thing you can do is rewrite t in the form. So we're integrating with respect to t. So we're going to write, we'd like to have our integrand in the following form. So that when we integrate our integrand with respect to t, we can write a t to the n plus 1 divided by n plus 1 plus our arbitrary constant, where n is not equal to minus 1. So we have to be careful to note that. So 6, I'm going to write as 6 times t to the 0. 6 t to the 0 is 1. 6 times 1 is 6. So 6 is equal to 6t to the 0. So I can replace 6 with 6t to the 0, which is what I'm doing here. So now we can proceed to write the indefinite integral, which is 6t to the power of 0 plus 1 divided by 0 plus 1 plus an arbitrary constant. This gives 6t divided by 1 plus the arbitrary constant, which is equal to 6t plus the arbitrary constant. And we're done. What if you're required to find the indefinite integral of 6 by integrating with respect to x? Integrating 6 with respect to x will require us to have, or it would be nice to have, our integrand in the form ax to the n. I can rewrite 6 in this form because 6 is the same thing as 6 times x to the 0. X to the 0 is 1. So you integrate 6x to the 0 with respect to x. And that gives 6x to the 0 plus 1 divided by 0 plus 1 plus your arbitrary constant, which is equal to 6x plus c. If you wanted to integrate 6 with respect to u or any other variable, this integrated 6 with respect to u, and then of course you want to have your integrand in the form a u to the n. U is now the variable in this case. So just be careful and note down what variable you're integrating with respect to, and take account of that when carrying your first step in such problems. And here's the final expression. We need to integrate this expression. So this expression is going to become the integrand. Integrating 5 over 2 t to the 5 with respect to t. It's always nice to have your integrand in the form a, because we're integrating with respect to t, so at to the n. What we have here is 5 over 2t to the 5, so it doesn't look like this form. So what you can do is rewrite 5 over 2t to the 5 as 5 over 2 times 1 over t to the 5, which is equal to 5 over 2 times t to the minus 5, which is equal to 5 over 2t to the minus 5. Now if I compare this to the form at to the n, at to the n, coefficient of, well, t to the n, in this case is 5 over 2, and that's a, n is 5, minus 5. So we can integrate 5 over 2 t to the minus 5 with respect to t easily. So integrating gives 5 over 2 t to the minus 5 plus 1 divided by the new index, which is minus 5 plus 1, plus the arbitrary constant. So this gives 5 over 2, so let me extend this, t to the minus 4, all divided by minus 4 plus the arbitrary constant. So the same thing as 5 over 2 t to the minus 4. Instead of being divided by minus 4, we can say times 1 over minus 4 plus the arbitrary constant, which is equal to, well, we can say, I could just break it down as this, 5 over 2 times t to the minus 4 times 1 over minus 4. And I can rewrite it as 5 over 2 times 1 over minus 4 times t to the minus 4 plus the arbitrary constant, which is 5 divided by minus 8 times t to the minus 4, so that's 5 divided by minus 8 times t to the minus 4 plus the arbitrary constant, which is the same thing as minus 5 over 8 t to the minus 4 plus the arbitrary constant. And you can also go a step further versus minus 5 over 8 times, instead of t to the minus 4, that's 1 over t to the 4 plus the arbitrary constant, which is then equal to minus 5 over 8 t to the 4 plus the arbitrary constant. The key thing that has been used here is the following law of indices. 1 over x to the n is equal to x to the power of minus n. 1 over t to the n is equal to t to the minus n. So here, 1 over t to the 4, same thing as t to the minus 4.